Today's lesson is about negations, and this is something I have definitely mentioned in our videos. So given a statement S, the negation of S is not S. This came up when we were doing truth tables and logical equivalence, for example. And we have seen a little bit about negations in the De Morgan's laws. So let me write these. De Morgan's laws, one of them says if you negate an and, this is logically equivalent to you take not P or not Q. And the other one is about negating an or. This is logically equivalent to not P and not Q. And I mentioned this briefly when we were doing truth tables. In fact, we proved one of them using a truth table, that when you negate an and, or if you negate an or, what happens, or this is the way I remember, is the and or the or switches to the other one, you see? And then you negate each expression. This is how I think about sort of distributing an not across an or across an and. Okay, now, how could we do this in an example? Well, here are two examples to negate, just practicing De Morgan's laws. The first is an and, the second is an or. And just thinking about this, 4 is prime, this one is false. 4 is less than 10 is true. When you have a false and you have a true and you and, this statement here is false. So when we negate, we will have a true statement, just as a comment. And then in the second one here, the empty set is an element of natural numbers. This is false. Empty set is a subset of natural numbers. This is true. We or, this statement is true. And when we negate, we will get a false statement. This is also a comment. Okay, here we go. Well, we negate. So this would say 4 is not prime. Or 4 is, now if you negate a less than, you are not less than. That would say greater than or equal to. Okay, so this is the negation in this first example. Now here we have an or, becomes an and then we just negate each of these. So this would say the empty set is not an element of natural numbers, and the empty set is not a subset of natural numbers. Okay? So both of these were De Morgan's laws for negating an or and negating an and. My next question is, how do we negate P implies Q? This is something we will actually need to do quite often this semester. Well, I can just, here is a truth table, right? And I can just think, well, I would just flip all the signs. So I know what it must be, not P implies Q is F, T, F, F. I just switch all the T's to F's and switch the one F to a T. But I want to express this as something that doesn't have this not all the way out in front, because when we have sentences, that's sort of hard to interpret like this. Well, I will do this in 2 steps. Let's show the implication is logically equivalent to, well, this will be not P or Q. And once we have this, we can use De Morgan's, which we just discussed. And this will give us an expression for this. Okay, this is the way I'm going to go about this. So let's show this, which we are almost there. All I need is a column for not P, and then a column for my final answer, not P. And then I can take not P or Q. Not P will go FFTT. And then not P Oh, not P or Q. Well, the only problem is when they're both false. Then the or is false, and every other time if one is true or both is true, the or is true. So here it looks like row 2 is the only time we have a false, and it's true everywhere else. Now, if you look at this, this is column 3 and 6. So as columns 3 and 6 have the same truth values, well, we see that P implies Q is logically equivalent to not P or Q. Okay? Now that I have this, and we have justified, we have proved with the truth table, I can just use De Morgan's, and I will know exactly what not P implies Q is. We will do it here. Not P implies Q. This is not, okay, then we have a not P or Q. Okay, now you see it's De Morgan's. This would be, well, if I take not of not P, this is just P. Not P will switch all the T's to F's and all the F's to T's, and then you take not again, and it switches all the T's back to F's and all the F's back to T's, so you land yourself back at P. So this is P, like this. So this is a way to write the negation of a P implies Q. It's P and not Q. We just saw that if you negate P implies Q, we get P and not Q. And we will now do 2 examples where we negate an implication, but I will just say that I did this by first realizing the implication as an or and then using De Morgan's laws, one of them, but you could also just show this directly using a truth table, just as a comment. Well, here we go. We have 2 implications to negate. This one is not about math, but it is still a statement, and it is still an implication. Let's do this one first. It says if the square root of 2 is a rational number, then 2 is a rational number. And this is our P, this is our Q. If we just think about this statement, well, it's true. This part, the if, is false, and so the implication is always true. When we negate, we will get a false statement. What we want here is P and not Q, which just says the square root of 2 is in Q and 2 is not in Q. So this says the square root of 2 is rational and 2 is not rational. Of course, this is a false statement. In fact, both of these are false. You add 2 falses, we get a false. Okay, now this one, as I mentioned, this isn't a math statement, but it is a statement and it is also an implication, and we can certainly negate. So if we look at this, Serena is smiling is our statement P. Serena is not sad is our statement Q. And again, to negate, we want P and not Q. And what does this say? It says Serena is smiling and Serena is sad. Because if you are not sad, then you are sad. So this is the negation of this implication. Next, let's discuss negating quantifiers. And this statement as it's written is a negation. And this is what we will start with, is a sentence. Let's first write it as symbols. So this says, not all integers are even. Well, in symbols, this would be not, let's say for all x and z, x is even. Okay? This is exactly this statement using the symbols we had discussed. Well, what is the negation? If it's not the case that all integers are even, then there is at least one integer that's not even. So I'll write that first, and then we will see what the symbols is. There is an integer that is not even. These two statements are saying the same thing. Okay. But what is this in symbols? Well, this one says the following. It says there exists an integer such that x is not even. And this is how negating quantifiers goes. Well, what did we realize here? I had a negation outside of a quantifier, and as I move it in, the quantifier turns to the other one. So if you negate it for all, it turns to there exists, and then the expression is negated. So let me write down what I just said. Negating quantifiers goes like this. If you negate for all x, p of x, and again, this would be for all x somewhere in some set, this is there exists x, not p of x. This is the one we saw in this example. But also, if we negate there exists x, p of x, this is, well, you bring the negation inside. When you do, this one turns into a for all, and then you negate. This is how we negate quantifiers. And we could have nested quantifiers, and we just negate sort of one step at a time. You move in the negation, and it changes the quantifier. You move it in again, it changes the quantifier, like this. Here are two examples. The first, we will make sure that we state the negation using words, and then the second one, I will just leave as it was handed to me, which is using symbols. So the first one, it says, there is a rational number that is not an integer. So let's write this in symbols just to practice. So we want to negate. So what we want is not there exists a rational number such that x is not an integer. This is what we want, right? This is the statement. There is a rational number that's not an integer, and we want the negation. Okay, well, this statement is true. 1/2, for example, is a rational number. That's not an integer. And so when we negate, this will be false. But in symbols, this there exists will become a for all. And then we move this negation to here. And if you negate and not, it becomes this. Okay? Now in words, what is this saying? This says all rational numbers are integers, which is definitely a false statement. Now, this next example, we have nested quantifiers. Let's just think, is this true or false? It says there is an integer such that for all integers, x times y is 2. And this order we have discussed, but x comes first. So there needs to be an integer that will work for all integers. And this will not be the case. Okay, well, there is no integer that will work for 0, for example. So in particular, there won't be one that works for all. But in any case, this is false. Okay, now let's negate. So if we negate this, we should get a true statement. And I mentioned how we do this. We can sort of move the not in one step at a time. The first thing I will do is move the not inside the there exists. This will become for all x and z. And then we have not out here. It would be for all y and z. xy is 2. Okay? And then we just move the not in one more time. And when we do this, this stays the same. Okay? When we move it inside, the for all becomes there exists. And then we negate xy equals 2. This would say x times y is not equal to 2. So this statement, for all integers, there exists an integer such that xy is not equal to. Here y may depend on x. Okay, well, yeah, you can just take y to be 0 and it doesn't even need to depend on x and it will work. But in any case, this is a true statement. And as we had mentioned, this one was false. When we negated, we got a true statement as we should. Here are 2 more examples to practice negating statements. Before we start, I also want to think about the truth of each statement because it's a nice exercise for us. Here, for all integers x, there exists an integer y such that x minus 2y is 0. Now, is this true or is this false? If we think about the way the quantifiers are nested, we pick y after x. So y certainly may depend on x. For all integers x, there exists a y which may depend on x such that x minus 2y is 0. Well, what would this say? This would say that x is 2y. Now, solving for y, we'd get at y is, this is sort of my side work to think about this problem, right? We get that y is x over 2. Okay, well, if I hand you an integer x, we know how to pick the y. It would be x over 2. But is this always an integer? No. So for example, if x is 1, there is no y such that x minus 2y is 0. There's no y. That is an integer. Okay, so this is a false statement. This statement is false. Okay, maybe I'll leave this sort of work at the top. It's fine because here is where I will negate. Okay, let's negate. Again, we have these nested quantifiers. I'll do this in 2 steps. First, this becomes a there exists. Okay, then I move the not in one more step, and this there exists turns into a for all. So I have there exists x and z such that for all y and z, and then we negate this part. X minus 2y is not equal to 0. Right? This is the negation. This is our final answer, and this is a true statement. There exists x and z such that for all y and z, x minus 2y is not equal to 0. We can just take x equal to 1. For example, it was the same one that the same x that sort of made this one fail makes this one true. Now this is written with words. I will leave my final answer also written with words. But one thing I want to discuss before I do, you notice it's a there exists, but we have this. Well, maybe I'll just underline this part. We have neither nor. What is neither nor? Well, neither even nor odd. It says you're not even and you're not odd. That's what this is saying. So let's write this in symbols to begin, because this will help us negating, and then we will go back and write a sentence. This says there exists x and z such that neither even, so this would be x is not even, and this is the nor, neither nor is not and not, like this. So, and x is not odd. Okay, well, this is a false statement. Okay, there exists x and z such that x is not even and x is not odd. This is false. When we negate, we will have a true statement. So we do this. This is what I'm interested in doing, is this negation. This says, okay, I have a negating there exists. This would be for all x and z. And then we negate this. X is not even and x is not odd. Now I am negating an and. This is De Morgan's, right? So I would have for all x and z, well, I negate this one, x is even. This turns to an or, and then negate this one. X is not odd. Okay, this would be x is odd. This says every integer is even or odd. This is the negation. And this is, as I mentioned, it's true. This one, false. This one, its negation is true. Here's my last example, negating. It is a great one to do at the end because we get to practice going from words to symbols, back to words, but also we will practice negating a quantifier, negating a implication, and these are all things we have discussed today. So the statement is, for all natural numbers x, if x is prime, then square root of x is not rational. As a comment, I will just say this is true. But here we go. This statement is written this way for all x and n. X is prime implies, well, that the square root of x is not an element of Q. This is this statement written with symbols. Now we want to negate. Okay, so this is what we are interested in. First, we have a quantifier. This would be there exists a natural number, and then such that it's not the case that x is prime implies square root of x is not in Q. Now, well, we have to remember, how do we negate an implication? If I call this P and I call this Q, and maybe I'll put it down here in a box, if we negate P implies Q, this is P and not Q. Okay, this is what we discussed. Well, here we go. This would say there exists x in natural numbers. Now I negate this, So I need such that x is prime, and I'll do it in symbols first. The square root of x is in Q. So this is the negation. And then in words, it says there is a natural number x that is prime and square root of x is rational. This statement in blue is the negation of this black statement. And this statement is false, well, as it should be. I mentioned this was a true statement. We negate a true statement, we get a false statement. Thank you.